February 25, 1945. Tsuchiura Airfield, Ibaraki Prefecture, Japan. The morning air carried the acrid smell of aviation fuel and burnt metal as Lieutenant Toyoda Takago, naval aviator and design engineer at the Yokosuka Naval Air Technical Arsenal, approached the object that had occupied his thoughts for the past 72 hours. Before him sat a Vought F4U-1D Corsair, Bureau number 57251, code number 69, its distinctive inverted gull wings bent in that peculiar angle that American pilots called the bent wing bird. The aircraft had belly landed in a rice paddy just outside Tsuchiura 3 days earlier, its Pratt & Whitney R-2800 double Wasp engine trailing smoke, its pilot desperately searching for any flat surface, as fuel starvation forced him down onto enemy soil. The American pilot had survived the landing and was now a prisoner, but his aircraft, remarkably intact despite the crash. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Had become something far more valuable to the Imperial Japanese Navy than another captured aviator. It represented an education in American industrial philosophy that would profoundly challenge everything Japanese engineers understood about fighter aircraft design, manufacturing capability, and the brutal mathematics of modern warfare. Takago ran his hand along the Corsair's metal skin, feeling the precision of American riveting, the quality of materials that his nation could no longer obtain in sufficient quantities. The aircraft bore scars from anti-aircraft fire and the violent impact with waterlogged earth, but even damaged and grounded on foreign soil, it emanated a sense of overwhelming material confidence that stood in stark contrast to the increasingly desperate improvisations characterizing late-war Japanese aircraft production. What Takago and his colleagues would discover as they systematically examined, repaired, and eventually flew this captured Corsair would reveal an uncomfortable truth that went far beyond simple, in technical specifications or performance numbers. The F-4U represented not merely a superior fighter aircraft, but tangible evidence of an industrial capacity so vast, a material abundance so complete, that Japan had been competing in an entirely different category of warfare from the beginning. The lessons learned from this single captured machine would arrive too late to alter strategic outcomes, but they would document with professional precision exactly how overwhelming American advantages had become by the war's final months. The story of captured American aircraft in Japanese hands begins not with this particular Corsair's emergency landing, but with the Imperial Japanese Navy's systematic yet increasingly desperate attempt to understand enemy capabilities through technical intelligence gathering as the Pacific War progressively turned against Japan throughout 1943 and 1944. By early 1945, when the Corsair force landed at Tsuchiura, Japanese forces faced a strategic situation that had deteriorated beyond any realistic possibility of military victory. American forces had recaptured the Philippines, subjected the Japanese home islands to sustained strategic bombing, and established air superiority so complete that daylight operations by Japanese aircraft had become extraordinarily dangerous. Material shortages plagued every aspect of Japanese war production, from high-grade aluminum alloys to aviation fuel to trained pilots capable of extracting maximum performance from increasingly marginal aircraft. Yet, despite these overwhelming disadvantages, or perhaps because of them, the Imperial Japanese Navy maintained a professional and systematic approach to technical intelligence gathering that continued functioning even as the broader war effort collapsed. The Yokosuka Naval Air Technical Arsenal, located approximately 13 miles south of Yokohama on Tokyo Bay, served as the primary center for evaluating captured Allied aircraft and reverse engineering foreign technology that might offer tactical advantages or technical insights applicable to Japanese designs. Toyoda Takago, one of the designers working in the foreign technology program at Yokosuka, later recalled the systematic nature of Japanese technical intelligence operations. The Japanese Army Air Force sent out most field recovery teams, subsequently supplying the Imperial Japanese Navy Air Force with copies of their reports and lending them captured aircraft as desired. The single team Takago remembered the Navy dispatching independently went to Burma, to study a crashed de Havilland Mosquito light bomber. But the Naval Technical Arsenal would receive aircraft recovered throughout the southern areas and would dispatch teams to crash sites in areas under Japanese control, including Okinawa, where a Grumman F-6F Hellcat had been recovered following American carrier raids in October 1944. British carrier raids in the Netherlands East Indies earlier that year had yielded a Grumman TBM-1C Avenger torpedo bomber. Yokosuka's specialists expressed surprise at the extremely strong construction quality they observed when examining the Avenger. The systematic examination of captured Allied equipment revealed consistent patterns that troubled Japanese engineers who understood the implications. Every major aircraft type captured and evaluated demonstrated similar characteristics: exceptional build quality using premium materials, sophisticated systems integration, robust construction that prioritized survivability over weight optimization, and manufacturing precision that maintained tight tolerances across thousands of production aircraft. The Imperial Japanese Navy had recovered flight manuals for various American aircraft types, including the consolidated B-24 Liberator heavy bomber recovered in summer 1944. They had flown captured F-6F Hellcats in evaluation flights. Japanese Army units had flown various captured types including Brewster Buffalos, Hawker Hurricanes, Boeing B-17 Flying Fortresses, and Martin PBM Mariner flying boats. Flying experience and detailed ground studies were compiled into comprehensive technical reports distributed to operational units and design teams, though Takago noted that because specialists were preoccupied with their own design work, studies of foreign aircraft remained fairly basic until very late in the war, when a special section of 3 officers and 12 to 14 men was formed specifically to track foreign technology. The Corsair that landed at Tsuchiura on February 25, 1945, was not the first F-4U to fall into Japanese hands. Japanese forces had captured at least one other Corsair fairly late in the war, and possibly a second example. Historical records indicate that American forces subsequently recaptured a Corsair near the Kasumigora Flight School in 1945. The Japanese had repaired this aircraft by covering damaged wing sections with fabric and using spare parts cannibalized from other crashed F-4Us recovered in the area. The evidence of fabric repairs and component scavenging indicated that Japanese engineers had attempted to restore at least one Corsair to flying condition, though whether they successfully completed flight testing remains unclear in available documentation. The recovery operation for the Tsuchiura Corsair followed established Japanese procedures for securing valuable captured equipment. Within hours of the forced landing, military personnel had cordoned off the crash site to prevent damage or sabotage. Initial assessment teams examined the aircraft carefully, noting the extent of battle damage, crash impact damage, and which major components remained serviceable. The Corsair had executed a wheels-up belly landing in soft ground, which absorbed much of the impact energy and prevented the catastrophic structural failure that would have rendered the airframe irreparable. The massive Pratt and Whitney R-2800 engine had sustained damage, whether from combat or the forced landing remained unclear, but the basic airframe structure appeared sufficiently intact for possible restoration. Japanese recovery teams arranged for the aircraft to be carefully transported from the rice paddy to nearby Tsuchiura airfield, where facilities existed for more detailed technical examination. The proximity to both Tsuchiura airfield and the Kasumigora naval aviation facilities made this location ideal for initial assessment before potentially transferring the aircraft to Yokosuka Naval Air Technical Arsenal for comprehensive evaluation. Lieutenant Toyoda Takago arrived at Tsuchiura as part of the evaluation team dispatched from Yokosuka. His role combined practical engineering knowledge with design experience, making him ideally suited to assess both the Corsair's technical characteristics and potential insights applicable to Japanese aircraft development. Takago approached the examination with professional curiosity, tempered by an engineer's understanding that captured equipment often revealed uncomfortable truths about relative industrial capabilities. The F4U-1D Corsair that lay before him represented the culmination of American fighter design as it had evolved through 3 years of Pacific combat. The Vought F4U had entered combat in February 1943, with Marine squadrons operating from Guadalcanal, where it quickly established superiority over the vaunted Mitsubishi A6M0 that had dominated early Pacific air combat. By February 1945, when this particular example force landed at Tsuchiura, the Corsair had compiled a combat record that Japanese intelligence services understood clearly, despite official propaganda. Over 2,000 aerial victories against approximately 189 combat losses, an exchange ratio exceeding 11-1 that stood as the best of any American fighter in the Pacific theater. The most immediately striking feature of the Corsair was its distinctive inverted gull wing design, a configuration chosen not for aerodynamic performance, but to solve a practical engineering problem. The massive R2800 engine required a large diameter propeller to absorb its substantial power output efficiently. Mounting this large propeller, while maintaining adequate ground clearance with conventional straight wings, would have required exceptionally long and heavy landing gear. The inverted gull wing design allowed the landing gear to be shorter and lighter, while still providing necessary propeller clearance, simultaneously reducing drag by allowing the landing gear to attach at the wing's lowest point, where it could be mounted perpendicular to the airflow. Takago examined the wing structure carefully, noting construction techniques and material specifications. The wing employed conventional aluminum alloy construction with ribs, spars, and stressed skin, similar in basic approach to Japanese designs. But the quality of materials immediately stood out. The aluminum alloy showed no signs of the brittleness or inconsistent properties that increasingly plagued Japanese aluminum production as strategic materials became scarce. Surface finish quality appeared uniform across the entire wing, indicating precision manufacturing maintained throughout production rather than deteriorating as factories struggled with material shortages and inadequately trained replacement workers. The wing incorporated flush-riveted construction on surfaces exposed to airflow, minimizing drag through attention to manufacturing details that required both precise tooling and skilled workers. Japanese engineers understood the aerodynamic benefits of flush riveting, but found it difficult to implement consistently in production, given wartime manufacturing constraints. The Corsair's wing demonstrated that American factories maintained flush riveting as standard production practice across thousands of aircraft, not as a special feature reserved for select examples. Control surfaces received particular attention during Takago's examination. The ailerons, elevator, and rudder all showed evidence of careful design and quality construction. Fabric-covered control surfaces used materials and techniques that Japanese engineers recognized as superior to increasingly marginal fabric available for Japanese production. Metal-framed structures underlying the fabric covering showed no signs of corrosion or material degradation, despite the aircraft's operational service and crash landing. Hinges, bearings, and control linkages all functioned smoothly despite crash impact, testament to robust engineering that built in substantial safety margins. The fuselage construction revealed American design philosophy in striking detail. The semi-monocoque structure employed formed aluminum skin panels, attached to internal frames and stringers, creating a structure that distributed loads efficiently while maintaining reasonable weight. But what impressed Takago most was not the basic structural approach, which resembled Japanese techniques, but rather the completeness and sophistication of systems integration throughout the fuselage interior. The cockpit represented perhaps the most revealing aspect of American design philosophy. Takago carefully examined the instrument panel, noting the comprehensive array of gauges, switches, and controls. Japanese fighters typically mounted essential instruments in relatively sparse arrangements that prioritized simplicity and direct pilot control over automated systems. The Corsair cockpit demonstrated a fundamentally different approach. Instruments were logically grouped by function, with flight instruments clustered centrally where they fell naturally within the pilot's scan pattern. Engine instruments occupied a separate grouping, as did communication and navigation equipment. The ergonomic consideration evident in cockpit layout impressed Takago, who understood that pilot fatigue directly impacted combat effectiveness during extended missions. The seat provided substantially better cushioning than typical Japanese fighters, important for missions that might extend beyond 4 hours. Visibility from the cockpit, even in the F4U-1D configuration with its raised turtleback behind the pilot, exceeded what Japanese fighters offered. The canopy provided good forward and lateral visibility, though rearward visibility remained somewhat restricted compared to later bubble canopy variants. The instrument panel incorporated sophisticated systems that reflected American emphasis on reducing pilot workload through automation. The R2800 engine employed an automatic mixture control system that adjusted fuel-air ratio based on altitude and power setting, eliminating the constant manual adjustment Japanese pilots performed. An automatic supercharger control managed boost pressure without pilot intervention. These automated systems reduced pilot workload significantly, allowing concentration on tactical situations rather than constant engine management. The electrical system revealed another dimension of American industrial capability. The Corsair employed a 24-volt electrical system with substantial capacity, powering not only engine starting and basic lighting, but also sophisticated radio equipment, gun heating systems to prevent jamming at high altitude, and various other electrical accessories. Japanese fighters typically employed simpler electrical systems with limited capacity, reflecting both design choices and increasing difficulty obtaining reliable electrical components as the war progressed. Radio equipment particularly stood out during examination. The Corsair carried comprehensive communication equipment, including both very high-frequency and high-frequency radio systems for air-to-air and air-to-ground communication. Radio reliability had become a significant problem for Japanese forces, as component quality degraded and experienced maintenance personnel became scarce. The American radio installation demonstrated not only superior equipment, but also thoughtful installation that protected sensitive electronics from vibration, temperature extremes, and electromagnetic interference. The armament installation provided clear evidence of American material abundance applied to military aviation. The F4U-1D mounted 6 Browning M2 machine guns of half-inch caliber, with 3 guns installed in each wing outboard of the propeller arc. This heavy battery represented a deliberate choice to maximize firepower even at the cost of additional weight and complexity. Most Japanese fighters of the period carried lighter armament, typically a mix of machine guns and cannons totaling fewer weapons with less total ammunition capacity. Each Browning M2 was fed from a separate ammunition box built into the wing structure, with each box containing approximately 400 rounds. Total ammunition capacity of approximately 2,400 rounds across all 6 guns provided roughly 20 seconds of continuous fire at the combined cyclic rate, approaching 100 rounds per second. For comparison, the Mitsubishi A6M0 carried 2 7.7mm machine guns with approximately 600 rounds each and 2 20mm cannons with 60 rounds each, providing significantly less total firing time despite the heavier individual projectile weight of the cannon shells. The quality of the armament installation impressed Japanese engineers who examined the systems. Each gun was mounted in an electrically heated compartment to prevent freezing at high altitude, where temperatures could drop to -60 degrees Fahrenheit or lower. Spent cartridge cases and disintegrating belt links were collected through chutes and ejected through ports in the wing's lower surface, preventing them from damaging the aircraft or interfering with control surfaces. The entire system showed evidence of thoughtful engineering that anticipated operational requirements and designed solutions for potential problems before they occurred in service. Ammunition quality revealed another dimension of American industrial capability when Japanese engineers test-fired the guns. The half-inch caliber rounds used armor-piercing cores manufactured to consistent specifications, incendiary compounds that functioned reliably, and tracer elements that burned predictably. Examination of ammunition revealed uniformly high quality across all rounds, with no evidence of the lot-to-lot variation that increasingly plagued Japanese ammunition production as quality control systems degraded under wartime pressures. The landing gear installation demonstrated American willingness to accept substantial weight in exchange for operational advantages. The main gear employed massive struts with oleo-pneumatic shock absorption that could handle carrier landing impacts repeatedly without requiring frequent overhaul. Japanese landing gear designs typically used lighter structures that required more careful handling and more frequent maintenance. The American approach reflected a design philosophy that prioritized operational reliability and maintainability over absolute weight optimization. Wheel brakes employed hydraulic actuation with substantial braking force. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this, allowing short landing rolls and positive control during ground operations. The tail wheel was fully steerable, linked to the rudder pedals for precise directional control during taxi. These features, seemingly minor in isolation, collectively represented significant advantages in operational flexibility and safety margins that translated directly into higher sortie rates and lower accident rates. The hydraulic system throughout the aircraft revealed sophisticated engineering applied to practical operational problems. Hydraulic pressure operated the landing gear retraction, wing flaps, cowl flaps for engine cooling, and wheel brakes. The system employed redundant components and intelligent failure modes designed to allow continued operation even if portions of the system sustained battle damage. Japanese hydraulic systems typically offered less redundancy and proved more vulnerable to combat damage. Most critically, Takago and his colleagues recognized that every system, every component, every aspect of the Corsair's design and construction reflected access to premium materials, sophisticated manufacturing equipment, skilled labor, and sufficient time for proper quality control. Nothing showed obvious evidence of material substitution forced by scarcity. Nothing reflected the desperate improvisations that characterized Japanese aircraft production by early 1945. The Corsair had been built exactly as American designers intended, using all specified materials and processes, with no apparent compromises forced by resource limitations or production pressures. This completeness, this fidelity to original design intent maintained across thousands of production aircraft, represented perhaps the most sobering revelation for Japanese engineers who understood that their nation faced an opponent whose industrial capacity exceeded Japanese capability by factors difficult to fully comprehend. The examination would continue for days as specialists systematically documented every measurable characteristic. But even from initial assessment, the fundamental truth was clear. America had not simply designed superior aircraft. They had created an industrial system capable of producing sophisticated weapons in overwhelming quantities while maintaining consistently high quality throughout production. The question facing Takago and his colleagues was not whether Japanese forces could replicate specific technical features observed in the Corsair. The question was whether Japan possessed the industrial infrastructure, material resources, and trained the workforce necessary to compete with an opponent whose manufacturing philosophy assumed unlimited access to strategic materials, sophisticated tooling, and sufficient skilled labor to maintain precision manufacturing standards across entire production runs. The Pratt and Whitney R2800 double Wasp engine that powered the captured Corsair represented the most significant revelation awaiting Japanese engineers as they continued their systematic examination. This massive 18-cylinder radial engine would force fundamental reassessment of what Japanese industry could realistically achieve given existing material constraints and manufacturing limitations. The R2800 consisted of 18 cylinders, arranged in 2 rows of 9 cylinders each around a central crankshaft, creating what American engineers called a twin-row radial configuration. Total displacement measured 2,804.5 cubic inches, equivalent to 45.958 liters. For direct comparison, the Nakajima Homar 18-cylinder radial engine that powered advanced Japanese fighters like the Nakajima Ki-84 displaced 1,990 cubic inches, or 32.6 liters. The American engine displaced nearly 40% more than its Japanese counterpart. But displacement alone failed to explain the profound performance gap between American and Japanese radial engines by 1945. When the R2800 was introduced in 1939, it was capable of producing 2,000 horsepower at standard boost settings, representing a specific power output of 0.71 horsepower per cubic inch. No other air-cooled radial engine in production anywhere in the world approached this figure when the double Wasp entered service. Even liquid-cooled engines, which typically achieved higher specific power outputs than air-cooled designs, barely matched the R2800's power density. By 1945, when this particular Corsair force-landed at Tsuchiura, production R2800 engines in the Dash 8 configuration used in F4U-1D aircraft were rated at 2,000 horsepower for military power settings and 2,250 horsepower for war emergency power, using water methanol injection. Experimental versions had been coaxed to produce 2,800 horsepower, though such ratings remained reserved for testing rather than operational service. The power progression represented steady evolutionary development rather than desperate attempts to extract more performance from increasingly marginal designs. Japanese engineers carefully examined the R2800's construction, documenting design features and manufacturing techniques with professional thoroughness. The crankshaft immediately commanded attention. Forged from high-grade steel alloy, it showed no signs of the material inconsistencies that plagued Japanese engine production as strategic materials became scarce. The crankshaft had been precisely machined and dynamically balanced to tolerances that Japanese factories found increasingly difficult to maintain, as skilled machinists were drafted for military service and replaced by inadequately trained workers. The cylinders employed forged aluminum alloy barrels with steel liners, conventional in basic approach but exceptional in material quality and manufacturing precision. Each cylinder head featured cooling fins so thin and closely spaced that they could not be cast or forged using traditional methods. Instead, American manufacturers machined the fins directly from solid metal, using gangs of milling saws automatically guided to ensure the bottom of grooves followed the contour of the head precisely. This manufacturing approach required sophisticated machine tools, trained operators, and sufficient production time to maintain quality standards. Japanese engine manufacturers understood the technique but found it increasingly difficult to implement consistently, given wartime production pressures. The valve train demonstrated sophisticated engineering throughout. Sodium-cooled exhaust valves handled extreme temperatures generated by high power output without the valve burning problems that plagued engines pushed beyond their design limits. Valve springs showed uniform temper and no signs of premature fatigue despite operational service. The valve actuation mechanism employed precise tolerances throughout, ensuring reliable operation across the engine's entire operating envelope from idle to maximum continuous power. The supercharger installation revealed American engineering sophistication applied to solving the problem of maintaining power output as altitude increased. The R2800 employed a two-stage, two-speed mechanical supercharger with an intercooler between stages to reduce compressed air temperature. This configuration allowed the engine to maintain high power output to altitudes exceeding 30,000 feet, where Japanese single-stage superchargers struggled to provide adequate boost pressure. The intercooler represented particularly sophisticated engineering. Compressed air from the first supercharger stage passed through a heat exchanger cooled by ram air, reducing temperature before entering the second stage. Lower air temperature increased density and prevented destructive detonation that could destroy an engine within seconds. Japanese engineers understood intercooler theory but had never successfully implemented such systems in production radial engines, partly due to the complexity and precision manufacturing required, partly due to material limitations that made reliable high-temperature components difficult to produce consistently. The supercharger drive mechanism employed sophisticated gearing that allowed the pilot to select between two speed ratios, optimized for different altitude ranges. At lower altitudes, where manifold pressure could be maintained with lower supercharger speeds, the low gear setting reduced parasitic power loss and improved fuel efficiency. At higher altitudes, where maximum boost was required, the high gear setting drove the supercharger faster, maintaining manifold pressure as ambient air density decreased. This two-speed capability provided significant operational advantages, but required precise gearing and reliable clutch mechanisms that added complexity and manufacturing challenge. The ignition system employed dual magnetos, providing redundant spark to each cylinder through 2 spark plugs per cylinder. This dual ignition configuration ensured reliable ignition even if one complete ignition system failed, critical for over-water operations, where engine failure meant almost certain death or capture. The magnetos themselves represented sophisticated electrical devices, requiring precision manufacturing and high-quality materials throughout. Japanese magnetos had become increasingly unreliable as component quality degraded, creating operational problems that no amount of maintenance could fully address. The fuel injection system demonstrated American commitment to precise engine control. Rather than using carburetors that could experience fuel flow disruption during negative G maneuvers, the R2800 employed direct fuel injection that maintained consistent fuel delivery regardless of aircraft attitude. The injection system required precision-manufactured components and reliable fuel pumps, but delivered superior performance and eliminated carburetor icing problems that could cause engine failure during combat maneuvering. Most revealing to Japanese engineers examining the R2800 was not any single advanced feature, but rather the consistent quality evident throughout every component. Every part appeared to be manufactured to exacting specifications using premium materials. Nothing showed evidence of substitute materials pressed into service because specified materials had become unavailable. Nothing reflected the compromises that Japanese engine manufacturers accepted as unavoidable given wartime constraints. The R2800 had been built exactly as designed, using all specified materials and processes, maintained across not dozens or hundreds but tens of thousands of production engines. By the time production ended in 1960, Pratt and Whitney and its licensees would manufacture over 125,000 R2800 engines, one of the largest production runs of any single aircraft engine model in history. This massive production volume achieved while maintaining consistently high-quality standards throughout represented industrial capability that Japanese engineers understood their nation simply could not match given existing infrastructure and resource availability. The propeller installation demonstrated similar attention to engineering sophistication. The Corsair employed a Hamilton standard constant-speed propeller with 4 blades, each blade measuring over 13 feet in length, to efficiently absorb the engine's substantial power output. The constant speed mechanism automatically adjusted blade pitch to maintain selected propeller RPM, regardless of airspeed or power setting, dramatically reducing pilot workload compared to manually controlled propellers that required constant adjustment to maintain optimal efficiency. Japanese engineers examined the propeller hub mechanism carefully, noting the hydraulic actuation system, precision bearings, and robust construction throughout. The engineering challenge of creating a reliable constant-speed propeller mechanism that could withstand the tremendous centrifugal forces, vibration, and variable loads imposed during operation was substantial. American manufacturers had clearly solved these problems and implemented constant-speed propellers as standard equipment across their fighter production, while Japanese fighters typically employed simpler manually controlled propellers that required greater pilot attention and delivered inferior efficiency across the flight envelope. After days of detailed ground examination, Japanese engineers faced a critical decision: attempt to repair the Corsair sufficiently to conduct flight testing or limit evaluation to ground-based examination. Flight testing would provide invaluable performance data and allow direct comparison with Japanese fighter types under controlled conditions. But restoring the damaged Corsair to airworthy condition presented substantial challenges given Japan's deteriorating industrial situation. The R2800 engine had sustained damage, though whether from combat action or crash impact remained unclear. Japanese engine specialists examined the power plant carefully, assessing which components could be salvaged and which required replacement. Some damaged parts could potentially be repaired using available machine tools and materials. Others would require components that simply did not exist in Japan and could not be manufactured given existing capabilities and material constraints. Historical records indicate that Japanese forces did attempt repairs on at least one captured Corsair, using fabric to patch damaged wing sections and cannibalizing parts from other crashed F4Us recovered in the area. This evidence suggests that Japanese engineers made genuine efforts to restore a Corsair to flying condition, recognizing the intelligence value of flight testing. However, whether they successfully completed these repairs and conducted actual flight testing remains unclear in available documentation, with some sources suggesting test flights may have occurred, while others indicate the aircraft remained grounded. The challenges facing Japanese repair efforts were formidable and reflected the broader industrial constraints plaguing all Japanese military production by early 1945. High-octane aviation fuel meeting American specifications was essentially unavailable in Japan. The Corsair's R-2800 engine was designed to operate on 100-octane fuel or higher, while Japanese aviation fuel production struggled to maintain even 91-octane ratings as refining capacity deteriorated under sustained American bombing. Operating the R-2800 on lower octane fuel risked catastrophic detonation that could destroy the engine within minutes. Replacement parts for damaged components were non-existent. Every bearing, every gasket, every electrical component was manufactured to American specifications using American materials. Japanese workshops could attempt to fabricate replacement parts, but matching original specifications without proper tooling, materials, or technical documentation was extraordinarily difficult. Each improvised repair introduced potential failure points that could cause catastrophic malfunction during flight testing. Lubricants posed another significant challenge. The R-2800 required specific oil formulations to operate reliably under the extreme temperatures and pressures generated by high power output. Japanese lubricants were formulated for Japanese engines operating under different conditions. Using incorrect lubricants risked accelerated wear or outright failure, but obtaining proper American lubricants was impossible given the strategic situation. Even if repair challenges could be overcome and the Corsair restored to some approximation of airworthy condition, the strategic situation by February 1945 made flight testing extraordinarily dangerous. American carrier aircraft ranged across the Japanese home islands with near impunity. Any flight risked interception by American fighters that would certainly attack what appeared to be a hostile aircraft, regardless of whether it carried Japanese markings. The Corsair's distinctive silhouette might cause momentary hesitation, but American pilots would quickly recognize a Corsair flying from a Japanese airfield as a threat to be eliminated. Despite these formidable obstacles, the historical evidence of fabric, repairs and component scavenging indicates Japanese engineers made serious attempts to restore the captured Corsair. The effort reflected professional dedication to technical intelligence gathering, even as the broader war situation collapsed around them. Whether these repair efforts succeeded sufficiently to enable flight testing cannot be definitively confirmed from available records, but the attempt itself demonstrated Japanese understanding that flight testing would provide crucial performance data impossible to obtain through ground examination alone. If flight testing did occur, Japanese test pilots would have experienced the same revelations that their German counterparts documented when flying captured P-51 Mustangs and P-47 Thunderbolts on the other side of the world. The Corsair's handling characteristics would have demonstrated the harmony of properly engineered flight controls, with aileron, elevator, and rudder forces balanced across the entire speed range. Roll rate would have exceeded any Japanese fighter then in service, allowing rapid direction changes critical for both offensive and defensive maneuvering. High-altitude performance would have revealed the decisive advantage provided by the R-2800's two-stage supercharger, maintaining power where Japanese fighters struggled with rapidly degrading performance as altitude increased. Speed trials would have confirmed the Corsair's significant velocity advantage. The F4U-1D achieved approximately 415 miles per hour at optimal altitude, substantially faster than the Mitsubishi. A 6M0's approximately 331 miles per hour, or even the more advanced Kawanishi N1 KJ Shiden's approximately 369 miles per hour. This speed advantage allowed American pilots to dictate engagement terms, attacking when conditions favored them and disengaging when threatened, fundamentally undermining Japanese tactical flexibility. The Corsair's structural strength would have complete 2,000 per, impressed test pilots familiar with lighter Japanese fighters. The F4U was substantially built with significant safety margins, engineered into critical structural components throughout the airframe. This robust construction allowed the aircraft to sustain battle damage that would have destroyed lighter designs and still return to base, directly translating into higher pilot survival rates and better aircraft availability for subsequent missions. Most critically, flight testing would have revealed that the Corsair's superiority stemmed not from revolutionary technology or secret weapons, but from systematic application of sound engineering principles, supported by unlimited access to premium materials, sophisticated manufacturing equipment, and trained personnel. The R2800 engine was not a miracle of German jet propulsion or rocket technology. It was simply an exceptionally well-designed conventional piston engine, properly manufactured using appropriate materials, maintained by skilled mechanics with adequate spare parts and tools. The airframe was not constructed from exotic alloys or secret compounds. It used conventional aluminum construction, but executed with precision manufacturing and quality materials, maintained consistently across production. This realization carried profound psychological impact for Japanese engineers and pilots who understood the implications. Japan was not losing the air war because American pilots possessed superior skills or because American designers had discovered revolutionary technologies. Japan was losing because American industry could design adequate equipment and produce it in quantities that rendered Japanese qualitative advantages increasingly irrelevant, while simultaneously maintaining quality standards that Japanese factories could no longer achieve, given resource constraints and infrastructure degradation. The captured Corsair at Tsuchiura served its most important function not through any tactical intelligence it might have provided, but as undeniable physical evidence that comprehensively documented the dimensions of Japan's industrial disadvantage. Every precisely machined component, every premium material, every sophisticated system represented capabilities that Japanese industry had never possessed at sufficient scale or could no longer maintain given the strategic situation.